So I'm really glad to have Colin presenting here. Colin got a mathematics degree at Trinity College in Dublin, and then he did a PhD at Fontainebleau in the geostatistics group led by Matron. But if I remember well, Georges Matron was not your advisor. But I mean, you've been in the home place of geostatistics. And I think Colin is one of these rare examples of people having pretty much an industry career. He worked with BP, with Roxar, and now he's been with Schlumberger for a couple of years. But he always kept doing research. And he always kept to do applied mathematics to solve geoscience problem. And I think I'm really looking forward to his talk to learn what he's been doing recently. I think, yeah, a few years ago I heard you saying, oh, I'm being paid for having fun and doing mathematics and trying to do something with it, and that's a great job. And so I'm really happy that you're going to share that with us. Thank you, Colin.
Well, I'm an extraordinarily boring speaker, so you can probably go back to sleep. It's going to be absolutely fine. Let's see if we got this thing going. Okay, so basically today I'm going to talk about trying to use machine learning without big data. Really, this is sort of, the stuff I'm going to look at is really a very simple model. You've seen a lot of stuff about GANs and so on. Well, I'm really in the other end of the spectrum today. I'm going to talk about something that's almost like, not a replacement, but in the same world as Gaussian simulation. It might sound very boring, but actually it's still really rather important in the modeling world. We tend to have to do it, especially in the oil industry. So that's the kind of topic I'm interested in. I'm going to speak very briefly about realizations and scenarios. Then I'm going to introduce the algorithm that we're going to work on. I'm then going to show how it can be sort of used a little bit in the world of scenario modeling, or how we can do some scenario modeling with Ember, and then maybe finish if I get that far. Okay, so for me, a scenario basically is a geoscientist has got some questions that they need to answer about the Earth, right? And so they form a conceptual model in their head to deal with that problem. And that conceptual model eventually has to become a mathematical model, which eventually leads us to realizations. Now, I'm going to take a narrow definition of that. Scenarios basically are clusters of realizations that emphasize a particular feature that the user is going to give and say, let me insist that this feature is respected. And that is the way they address questions. So this kind of slightly weird view that scenarios are question answering comes from quite a bit of work over the years that I've been involved in or thought about. And so this is one example of a little mini experiment when I first joined Schlum in 2007. I was looking at the last time an old MPS algorithm that I had come up with a number of years before in a history matching context. So the history matching problem is, we could see, is very simple. It's basically, we've got an injector well in the middle, 4 producer wells. We produce for a year, build models that match history, and then try and predict the next year going forwards. Okay, so that was the idea. We started with a number of very different scenarios that you can see over on the left here. Here's my mouse going over here. So these are radically different looking things, some of which are completely absurd. And we want to see, can we history match? And if we history match, how well does it predict going forward? Okay, so the algorithm I was using was, like I said, it was an MPS, but it was a special MPS, which was also a Markov random field. And given that it's a Markov random field, it also has got a Gibbs distribution. And because of the Gibbs distribution, you can calculate the entropy. Now, if you know a bit about information theory, you know that entropy basically is a counter of how many realizations there are. So, for example, on a grid of size n with k colors, you've got k to the power of n possible images on that thing. And as n grows to infinity, that gets enormously large. Now, the number of realizations of two different figures of different entropy, the one with the higher entropy will completely dominate the number of realizations. So if we were to draw at random between sets of one entropy and sets of a higher entropy, the ones at the higher entropy will win every time. It'll always be drawn. Okay, so with that in mind, let's look at this over here. We've managed to history match with all kinds of realizations, and in fact, all of them, apart from the last completely nutty one, managed to history match. Yet when we looked forward to see which ones predicted well, only the ones that were quite close to the geology predicted well. Okay? So now the question is, given that we don't know the real geology, which history-matched realization should we be working with? And if we go with the classic geostats thing of sort of say, well, let's just pick a realization at random that history matches, and we use the logic of statistical mechanics, we end up picking the highest entropy, okay? Because that's the one that occurs over and over again. But unfortunately, the highest entropy has got nothing to do with geology in any sense. So that criteria is not likely to be successful. Excuse me. And that's what leads me to believe that the idea really is that what we're doing is we're taking almost a postmodern approach to modeling. We ask ourselves a question, we build models that allow us to answer that question, we move on, ask other questions, and we start to learn about a problem by nudging around it like that, rather than believing that there's some glorious uncertainty model that's going to answer everything. It's difficult to find glorious uncertainty models. With that, I'm now going to talk a little bit about this algorithm that I've been looking at for a while. It's a really simple method, primarily intended for stochastic simulation. What we try to do is estimate conditional distributions at all target locations, and it uses multiple input variables, which can be both observed data, but also simpler models. So for example, we're going to use kriging as an input into this model. And that's where it gets its name EMBER, because it's for embedded model estimator. So we're embedding models, and embedding is a way of trying to make sure that we don't double dip, we don't use information twice. So it's a two-step algorithm similar to the idea of regression kriging, for example, where you have a mean trend and a residual. And it's when you interpolate the residuals that you honor the data. In our case, what we're going to do is try to get an approximate conditional distribution at every location in space. So consider this case where we've got a number of data points, and we're trying to estimate at some other locations. We work out the distribution, the conditional distribution at these guys. Now, the one in the middle could be a bit ambiguous. It could be all kinds of things, but it might look like this. And it would look like that potentially if you'd got a fasces to the left and a different fasces to the right. And so what we were looking at in the middle was a kind of transition from one fasces to the other. You might get something bimodal. And the idea really is that I'm hoping that the envelope is going to work out, is it this kind of bimodal distribution, or is it something much more global or whatever? So that's the plan. Also, at the locations themselves, because this is trends, we're not actually going to get an exact distribution to start with at the data locations. We still have an approximate distribution. So we have to go on to the next stage in a simulation. This basically is the envelope, right? It's like the whole of the set of these distributions. And so the next thing we're going to do after this is to sample from the distribution. So our sampling basically is just a conditional model that passes through the envelope. And it can have things like discontinuities in it compared to a sort of standard Gaussian simulation. Okay. So mathematically, really the equation that's being used for this is my approximate distribution is the CDF of z less than z, basically, given my secondary variables y and my embedded models. Okay, now, to run this thing is fairly obvious. Basically, you calculate y and m at a location that you want to run, and then you work it out from this distribution which you've pre-calculated. But how do I train on that? Well, we do that in a fairly standard way, except for these embedded variables. So, for example, if my embedded model is kriging, and I'm training using a data location, now we know that kriging is exact at that location, so I'm not going to learn anything there. What I have to do is cross-validate. I leave that value out, I predict using kriging, and I'm learning in the machine learning method. I'm learning from the error that kriging makes. So I'm seeing how good or bad kriging is and weighing it according to how good or bad it is at predicting. And what I do to kind of make sure I don't overtrain is I actually do multiple estimates, like leave out all possible subsets of the data and cross-validate over and over again. So, in fact, when we come along to the estimate of the envelope, it's this problem over here on the right-hand side, which is a very low-dimensional problem. I'm using just my secondary variables at the location that I want to estimate, together with my embedded models, and I can have several of these models, okay? So at this point, I haven't used any random function at all. I might have some spatial content because of my embedded models, and I might use kind of spatial variables like x location, y location for the y's. So I have some spatial content, but no random function. And the only place a random function actually appears is when I sample. So I've never had to worry about things like non-stationarity, because the sampling, I can always do that in a stationary way. Okay. So going forward, I'm not going to distinguish between M, which was embedded variable, which, as I said, is no longer just a single number. It's actually an event from a random variable, or the Y values, which are outcomes, single observations of a random variable. But basically, they're all the same thing, and we can train happily on that. The method I use is a kind of slightly boring old random forest, but I do that for a very good reason, which I'll talk about in a moment. Basically, you know that a random forest is a set of trees, and if I want to predict at a target location, basically you find out where that value falls into each of the trees. The terminal node in a tree is actually a hyperrectangle in the space of secondary variables. And so I calculate, from each of those trees, I take the prediction from that hyperrectangle, and that gives me a distribution of estimates. Now, people who use random forests normally just take the mean of that, but we're going to hang on to the entire distribution, because essentially we've used secondary data, so it must in fact be a conditional distribution. And there's a theorem by Munchausen, who first wrote the paper on quantile random forest, which proves that this converges to the true conditional distribution. So we might as well use it, okay, and exploit that properly. Now, other people have used random forests for spatial prediction. In fact, it's become really popular. The first one I saw was Lee and Heap in 2011, but that was it didn't have any spatial variables in it. And we tried in 2016 with Ember. I first presented it at the Geostats conference. It wasn't called Ember, but I first presented it there with spatial information. But there has been other approaches. So Hengel, for example, uses the distance to each data point as an additional variable. And that's a nice idea, and it works for small numbers of data. But I'm going to show an example later where I've got 100,000 samples. Now, that would mean 100,000 variables, and that's kind of too much, right? A simpler idea, there's at least one common author in these two papers, so there's this kind of continuation, is to calculate the nearest k neighbors, and for each neighbor, use the value at that neighbor and the distance to that neighbor as variables and train on that. Now, bizarrely, actually, I did test that, and by way of proof, we've got a little bit of the code that I'd written in 2016 with the magic words, use neighbors directly, where I tried it out. And then after that, I dropped it. And I can't remember for the life of me why I dropped it, but it was something like an isotropy, right? You know, the nearest neighbor in the vertical direction is a very different behavior to horizontal directions, and it didn't really distinguish between those properly. So I think in 3D, it wasn't quite so spectacular. But anyway, really what I'm more interested in is simulation. And in simulation, I can use this notation here of a structural equation model. I don't know if anybody reads causality, the science of causality, but I've been very influenced in that, as you'll see, kind of moving on to the way I deal with scenarios. So you're writing this as a structural equation model, and basically to sample, my distribution is worked out from Ember, and all I need to do is to sample from the distribution on the right. And that basically is a uniform number. Now, the way I do that in the base Ember case is to generate a uniform random field. How do I do that? Easiest way is to generate a Gaussian random field and transform it to uniform, okay? So in other words, it's a Gaussian copula. But I have to remember that I must condition at the well locations, because I didn't get those perfect, right? So I have to do that, and that's what completes my conditioning. So let's have a look at examples. In a synthetic reservoir model that I made on the left-hand side, and I generated some seismic on the right, and we're going to look at it with 8 wells and 36 wells to see the effect of increasing information. Just how it was built, I started with an object model, which I'm no longer going to use. We just started with that to build it. There was some zones which are tidal shore face and other ones that are fluvially dominated. The chunk in the middle is a missing fault section, which you can see it's the red dotted line there crossing the fault. This is what the porosity looked like, and you can see they're very different. The shore face are very easy to predict. They're simple coarsening upward sequences. The other parts are much more complex to predict. Now, Ember does everything in one go. It doesn't break things out and model different zones at different times. So that's what we've got to remember here. Available data for this case, well, I've got a bunch of secondary seismic attributes, and I'm also going to use variables like distance to fault, like height above water contact, and so on, things which we can't normally use in ordinary geostats. Of the training variable on the left, all I've got, obviously, is just 8 wells, okay? So in the next slide, I'm going to show prediction using 8 wells. And on the left, we've got the true porosity. In the middle, we've got the Ember simulation. And remember, all of this is done with more or less one button click, basically just go, with a slider to kind of say what correlation length you want to have. Now, it looks too good to be true, and that's really because it's very simple. The shore face sands were extremely simple, so that's not hard to do. The channels are actually not as good as they look. When we see it in plan view, they're not spectacular at all with 8 wells. But from Ember, you also get the uncertainty model, which we can see is low uncertainty in the shore face and high uncertainty in the channels. One of the important things is that we've got the distribution. So this is a cross plot of one of the seismic attributes with porosity. And you can see that even with 8 wells, that's recovered really rather nicely. So long as our data are sample honestly, we will recover those distributions. Okay, that's by kind of default. And that comes from the envelope part. Okay, so let's just have a look at a blind well. So the blind well is a well, a 9th well that we're estimating from the 8. It's this one here, and that's shown in this column here, okay? Then I've got 5 Ember simulations here, 1, 2, 3, 4, 5. And you can see that in the shore face, they all look pretty much the same. Whereas they're really rather different to one another up in the channel zones. Now, the interesting one is this one here, okay? The red curve is not so interesting. It's just the truth, okay, written here. But the black curve is the envelope. So that's our estimated conditional distribution. And what we can see up here, it's black, and then gray, and then black again. And the color is the probability. So it starts with a high probability, okay, then low probability, then high probability. So it's saying it's either going to be shale or it's going to be high porosity sand, but it's not going to be in the middle. So it's actually finding a bimodal distribution here. And when I simulate, I'm going to be landing in one of those two, either in or out of channel, but nothing in between. Whereas down here, it's unimodal and extremely simple and extremely narrow. Okay? So we now have this envelope, and all simulations have to live within there. Just to show the effect of gaining information. So I've got a truth up on the left in a particular layer, and in the center. We've got the seismic below it, and you can see that the seismic picks out one of these channel complexes, the one on the right, but it doesn't seem to pick out the one on the left. Moreover, there's no wells that actually go through it. That one looks like it touches, but actually it just misses. Now, from Ember, of course, you can pick out all of the quantiles, the P10s, P50s. They come for free, and we can see them here. And you can see that none of them are picking out the channel on the left, but they're easily picking out the one on the right. And the simulation, likewise, you know, it has kind of blobs on the right, which are not channel-like, but they're kind of at least sand in the right place. And it doesn't see anything on the left. Now, if I move on to 36 wells, you suddenly see that you've got a gain in information. You now are getting channels on both sides, both in the simulation and in all the estimates of my quantiles. And interestingly, I don't know if you can see it very clearly, but there's some texture in here that really seems to come from the truth. And that obviously can't come from just the wells. So it means that we're picking out bits of information in the seismic that was not available in the 8 well. So we're actually learning in a nonlinear way from the seismic data as the amount of data increases. So to conclude section 2, I think the most important thing really here is points 3 and 4. There's no data transforms, no stationarity requirement up front. And point 4 is that when you've got very few wells, basically Ember just collapses down to becoming SGS, essentially, a Gaussian simulation. Admittedly with an inbuilt transform, but that's not a bad thing to do, because the only thing I've got in there is a hypothesis about my correlation length, and therefore the maximum entropy thing when all I know is a correlation length is a Gaussian model. So it's kind of doing a sensible thing in a sense. Also, I have shown that it does converge in the sense that as the number of data increases, this will converge to the correct value at any location. So it's a consistent estimate model. On the other hand, I haven't proved anything like optimality. I must admit, I haven't tried. Is this really the best way to incorporate data? There may be better ways. Okay, so on to the idea of scenarios. And it's a little bit lame, but again, it comes back to, I talked to a geologist and they've, say, got 3 wells in a field and they want to use Ember. And really, I designed it for cases where you got 150 wells. But forever, people are coming up to me with 3 wells and saying, what can you do with this? And I'm going, pfft. And then they give me the seismic and we calculate the correlation between their wells and the seismic, and it's 0 or 0.05 or something. And you kind of go, okay, run the model and out comes a Gaussian distribution, and they're very disappointed. So you go, okay, really this is the time to go back and start building GANs or something like that, okay? But maybe we can do something that's cheap and cheerful in the idea of let's explore scenarios. So the idea is, okay, I'm going to take one of your attributes, one of your seismic attributes, or maybe a geobody that you've interpreted, and put that and force that into my model, okay? And I thought of various ways of doing this, including one using optimal transport, actually. But the easiest way by far is to intervene. And this is, again, this causal modeling idea, to intervene on my sampling strategy. Now, interventions are a notion that Pearl, well, other people have thought of them before, but Pearl's book on causality is quite nice. And really, the idea here is that, you can actually look at things from a counterfactual perspective. You can say, I've got a realization and it has a certain type of behavior. Now, what if the seismic had a stronger influence, or what if that geobody was actually there in the first place? And you can increase the influence of the geobody and see the things change. So you're acting like in a way that's different to the original individual you started with. And of course, the interest in that for me is in things like history matching, because this is entirely parametric. So basically, we can switch on and off the influence of certain variables in a parametric way. Okay, so the difference, the new thing I've got to do is combine together this x, this variable x, and u of e. And the simplest possible way to do that is just to do a little mixture. To kind of, if x was Gaussian, I just run them as a mixture like that. Now, even if x isn't Gaussian, all I needed to do is have a mean 0, variance 1, and the thing seems to run reasonably okay. The problem is, x should be chosen to be independent. And that shows in this diagram here. If you're used to looking at these diagrams, that actually states that x is independent, because these diagrams here, the fact that you've got an arrow coming, both sides coming into z, mean that x must be independent of the y's. Now the question is, where am I going to find a variable that's completely independent of the things that I trained on, that still has information? Surely if it's got information, I'd want to train on it. So we've got to kind of relax this a little bit and say, we're going to do something dodgy. We're going to take one of our variables that we've already trained on and use that to influence the sampler. And that puts an arrow from y across to epsilon. But now we've got 2 arrows. We've got an arrow coming into z, and we've got an arrow coming into epsilon. And that means that epsilon is what's called a mediator, right? And that's kind of bad news, because it means that I'm no longer going to reproduce all my histograms perfectly. So it means that we're now in a situation that either me as the software developer is going to have to limit and sort of go, I'm only going to allow things go so far, or the user is going to take a risk. Today I'm going to show really extreme values where I'm going to push this rho value to very high numbers, which kind of are a little bit further than I reckon you should do in practice. But it's easy to see the pictures, you know, from a distance of what's going on. There is a kind of an escape route, which I've been trying, but I'm not going to show today, which is basically use a substitution random function. So basically, the variable y that I'm going to use, I pop it into some kind of randomizer, and that will give me at least linear independence. It's not full independence, but it'll mean that they're not correlated. So that's kind of start. There is a downside, is that you end up with random functions that are not ergodic, and that's not the best thing in the universe. So I'm still playing with that. But let's have a look at an example or two. First, a pretend one that we've done from before, and then a real case study. So in this one here, I've got a geobody. So in my truth situation, we have a layer where there's two channels in it. Again, as before, the seismic is not showing us everything. So we're only able to interpret one channel as a geobody, for example. We can't see the other one. So we want to include this geobody, but we don't want to lose the other thing, right? And I'm going to compare it in a kind of slightly nasty way with Gaussian co-simulation. I mean, you would never use Gaussian co-simulation for this. But it shows what can go wrong and why it doesn't go wrong when you do it in Ember, because you're just resampling within the envelope. So let me start with just 36 wells and nothing else. So far, I'm not using the body. Now, the Gaussian model with 36 wells is a little bit kind of all over the place. The Ember model, okay, it's no GAN, but you can see it does have things that are roughly channels in roughly the right place. They're not exactly channels, but I wouldn't be too ashamed of passing that over to a flow simulator. It's kind of okay-ish. Now let me take up the next step and include the geobody. And if I do that in the most obvious way, with co-simulation, I find the correlation coefficient and do a co-simulation using that correlation. Weird thing to do, admittedly, with a discrete object, but we can try it. And actually, it does nothing at all in the Gaussian case. But the Ember case, the obvious thing to do is take that and put it into my training. And if I put it into the training, because things learn non-linearly, actually it learns quite a lot. You can see the shape of that object being used, particularly in the areas where there's no wells. It's kind of going, yeah, this will do fine, right? It's because it seems to predict in other areas. So now I'm going to start forcing and cranking up the influence of this variable. And if I go up to 0.8, now you can see in the Gaussian case, yes, I am beginning to kind of ramp that in, but of course at the expense of everything else. And that's because the things outside the channel were zero. So a linear correlation would be a stupid thing to do because you destroy everything else. But if I'm doing that with sampling in the envelope, I don't really lose everything else. So you can see I am still maintaining the channel. And even if I go to the completely absurd value of 0.1, oh, wrong button. If I go on to the absurd value of 0.1, where the Gaussian model has just kind of collapsed completely. The noise, by the way, is what we call despiking. Anybody who's into the nitty-gritty of geostats will know what that is. But the Ember case is fine, and you can see the two channels. Actually, bizarrely, you can see it nicer than in the raw case. So that seems to work okay. With fewer wells, well, same situation. Again, you learn a bit less well with only 8 wells. But if I start ramping up the forcing, you see that actually, yeah, I can get that in there. And I'm not doing too much damage because I'm still within the envelope. Okay, things are smoothing out a little bit as I go very far. But if all I want is a scenario in this idea of playing games, then that's okay, so long as I can do many of these, and I can do, which hopefully we can. Cross-section, again, it's the same thing. You can see that with the Gaussian case, it starts losing its structure. You're losing the high porosity streak at the base, whereas in the Ember model, you're not. Okay, so a real case study. This was done with Pertamina in Indonesia. I was involved in this and modeled the main oil zone, which is kind of over here. This is hand-drawn pictures of what it looks like, so you can see it's fluvial in a deltaic type of environment. It's pretty thick, about 650 meters. They manually did 50 zones in this. And so with 650 layers, basically of 1 meter each, there's 300 wells in the south of the field. So the world I thought we'd probably be using Ember in originally. So this is nice. We've got a lot of data, 180,000 samples to learn from, which is good. So I'm only going to show one zone, right? The R13 zone. We've got a whole bunch of seismic attributes. The correlation with these attributes is unfortunately very low. It's onshore, not particularly great. So the Ember model is built with several seismic attributes, as well as a couple of embedded kriging, one long range, one short range, to figure out, what one is giving me the best kind of lengths, and a few geometric properties. And I wanted to test one other thing as well. If I look at the well locations and calculate a density of those, the number of wells per square kilometer, what we see is that there's high density in the crest of the field, and low densities both in the south of the field, which is where they want to extend into, and on the flanks. Now, wouldn't it be tragic if there was high porosity in the crest of the field? Because if you were to calculate the average porosity using those and apply that to the entire field, you'd get a biased value for your average prediction overall. And that in geostatistics is called the clustering problem, and we have to decluster, okay? So let's see, does Ember manage to decluster a little bit? So if I press go on this layer, the two on the left are the P50 and the uncertainty, which come directly from the envelope. And they're kind of come for free. So the P50 is like my interpolator. I then have to do a little bit of simulation. Now, in this case, we simulated two variables. We simulated net to gross and we simulated porosity. And as you can see, net to gross was a variable that essentially was zeros and ones. Not quite. There were some values just in the middle that were transitioning from pure sand to non-sand. And you can see that Ember produces a model which is essentially zeros and ones, right? So again, it's quite happy to respond with whatever thing you put into it. That's not saying it's a fascies modeler. It could fairly easily be modified to do, say, truncated Gaussian or even pluri-Gaussian. And I might get around to that one of these days. But it certainly does two fascies fairly nicely. And then I use that as a control on the porosity. Now, in fact, we didn't have to model net to gross. If I model porosity directly, you get more or less the same result. The simulations look a little bit noisy. Actually, the reality is a bit noisy. So I was happy with this, but the geologists were kind of, well, I'd like things to be a little bit smoother. So again, look at scenarios. Oh yeah, before I finish, how about this declustering business? At the bottom, you can see this curve here. And if you remember, I said, wouldn't it be terrible if? Well, this is well density. And when the well density is very low, the porosity is kind of lowish. When the well density is high, the porosity is high-ish. So we do have that clustering problem. And for the wells, that's the blue curve. However, very happily, Ember gives you the orange curve. So it actually follows exactly the correct track and has basically successfully declustered. It's putting lower porosity in the places that the wells tend to be suggesting lower porosity, even though the well density is changing from one location to the next. And you can see very clearly, this is the model of the full 650 meters. Now again, this is all modeled in one go. You don't have to break it out and model it zone by zone or anything like that. And you can see it's very clearly non-stationary with higher porosities up near the top. I don't know how to stop this connection thing. Gone. Okay, so you can see higher porosities up near the top, lower at the base, and again, a trend from one side to the other. Okay, they'd asked us to do some tests, so they kept 7 wells behind that they didn't give us until the end, and they wanted to see over the 50 zones, they wanted to calculate net pay over the 50 zones and see, what they were in the wells versus what we predicted in the wells. And that's what we're seeing here on the right. We have, 7 by 50, 350 points, and this is the net sand zone by zone. This is the true value, and this is predicted value. And these two are for the net to gross, and these ones are the equivalent porosity thickness. And you can see that our correlations are fairly good. In fact, our predictions were about 30% better than their previous model. And it's not that their model was bad at all. In fact, it was really rather good. But they had they had done a lot of work on this kind of stuff here. They'd done some manual interpretations of the channel fairways on a zone-by-zone basis for, and it took months, apparently, months of work on this. How do I get back? Yeah, okay. So, right. So I'm going to look at a couple of scenarios here. As I said, they kind of weren't so enthusiastic about the base case. They said it looks a bit too noisy, even though when you calculate it over a zone, actually the continuity is fairly decent. But in the first case, we've no intervention whatsoever. All I did was change the correlation length, perhaps a bit more than I'd be perfectly happy with. But you can see that the channel that they kind of prize sort of pops out by just increasing the correlation length, this channel in the middle. You can also do things like you can increase the net to gross. So I'm not forced to stay with the same value of net to gross. And you can do things like take one of the seismic attributes and say, look, let's force that one a little bit. So he took the one that was about the best. I think it had a correlation of about 0.13. Not spectacular. But there was something there, and there may be some residual information, even if the point-to-point correlation isn't great. And in fact, when you push that one, you see that channel coming back out there as well. Push it like a crazy person, and you can see it's very smooth, but again, that channel is nice and clear. And of course, we could have taken their model, and that was one of the things they asked for. And we see that you end up with realizations as well that look fairly plausible with their interpreted geobodies. Okay, good. Two last slides. Now, I didn't do a lot of study on this. This is a field called Groningen. And the base Ember case is up on the top left. And you can see it's kind of very noisy looking. But later I'm going to go into this little black box here just to show you why it's noisy. And then I took two seismic attributes and pushed them again, more than they should be pushed. But again, you're looking at it from far away, so you need to see that. This one is pushed in the positive direction as far as it can. And this one is pushed in the opposite direction, kind of as far as it can. So they're kind of interpreting the seismic slightly differently, but within the envelope. And the last one here is a distance to fault. Now, that sounds like a mad thing to do, especially take that and push it very hard. But, again, that's down to the geologist. The geologist will say, that's crazy, you're not going to want to do that. I might want it a little bit. Or maybe you're going to take it, put it into your simulator, and your simulator says, no, that's crazy, I don't want to do that. But in this case, what was kind of interesting is, if I look at from the envelope, the uncertainty in that layer in the reservoir, you can see that, in fact, the uncertainty near the faults is much higher than away from the faults. I'd been telling people for ages, throw in things like distance to fault, and it never made a blind bit of difference. But for a number of the layers in this reservoir, bang, it jumps out. This is an uncertain variable. There is definitely a response to the faults in these layers, which was kind of interesting. Zoom in, and now you can see these kind of white blobs with the dots in the middle are the wells, and you can see they're in clusters, which is kind of nice. So we've got wells very close to one another, and what you can see is that I've got red values, I've got green values, I've got pink values, I've got all different colors right beside one another. So there really is a lot of heterogeneity at a fine scale here. And that's why the overall model looked quite so noisy. Now, when you look at it here, it looks okay. And in fact, this fits in fairly nicely. Again, you see all that heterogeneity, reds, yellows, greens. But if you look at all of them, they all seem to fit the distribution fairly nicely. Even the bizarre distance to fault, it doesn't look out of place. Everything kind of fits the data well. All of them reproduce the histogram. Now, because I've pushed things to the extreme, they're perhaps not honoring the cross correlations as well as they should, right? That's the downside. But other than that, it's not terrible. Last thing is to note the uncertainty in this one has got that weird-looking blob in one region, and the reason for that is that one of my input variables was fault block. So that particular fault block, it does have a couple of wells in it, but those wells are right beside a fault, and we know that beside the fault is very noisy. So it's kind of downweighting that information. That fault block is underinformed, uncertainty. Okay. Now, conclusions. Let's focus on the bad stuff, will we? The problem is it's difficult to find an intervention that's really independent of training variables. So somebody's going to have to control this, either the user themselves or me as a software policeman will sort of go, I'm not going to let you go too far. And I'm not 100% sure what way to do with that, because we haven't released the intervention stuff in the software just yet. And to show the result of that, actually, when I do push Ember to the crazy limit, you can see there's the truth. The COSIM, of course, has just produced garbage. The Ember is not garbage, but you can see here it's thickening up the channels a bit too much, right? And so that's wrong, but maybe it's okay as a scenario, all right? The alternative, as I said, is I can solve this, I'm pretty sure, by putting a substitution random function in the vertical direction. So just randomizing the response to the seismic in 1D. And I think that'll kind of reintroduce the right variogram in that direction. If there's good things, it's fast, simple to use. It relaxes the requirements for stationary. It is grid-free, even though the current implementation in Ember is not. But I use it in other places as well without a grid. The further developments are, well, really try and think how to make sure that the intervention is not so much of a mediator. How do I kind of free that up a little bit? One thing I'm about to start on, actually, is looking a bit at production data. You know, so if we wanted to use this as a member for ensemble creation, the fact is that interventions are parametric. So you could get something simply calling it, switching up and down the influence of one intervention variable versus another, and so on. So basically, that's the way I can see this potentially going forward. We've already done a tiny bit of work in integrating forward stratigraphic models. It's relatively hard, but we've had at least one result that's kind of okay, and it's something we want to explore a bit. Okay, I think that's it.
Thanks, Colin, for the excellent presentation. Any questions? Yes, Grégoire.
Thank you, Colin, for this really nice presentation. So if I understand well, your model has two components. One of them is the embedded model. One of them is the distribution from the random forest. And my question is, what if you turn off the embedded model? And you turn it off and you just have the covariates driving whatever you simulate. What do you lose then?
I kind of slightly alluded to that in one question. I do have possibly a slide or two that answers that somewhere in my backup set, but I've no idea how to get to that. So I can't really show. Frankly, the problem is if you switch it off, then you've got a random forest without any spatial content, okay? Now, does it work? Yeah, reasonably well. But I definitely have cases that you can show that actually there's a gain by knowing the spatial content, right? That kriging itself is a pretty decent predictor, and that there is not enough, for example, when your seismic is a little bit weak, but you do have a reasonable number of wells, then kriging is the dominant. In fact, even in the model that I showed, the pretend model, right? The seismic was the strongest variable in the channel sands. Kriging was pretty hopeless there. But you could see that I was already able to make superb predictions with 8 wells in the shore face. That was because of kriging, right? It was the embedded model that was doing that. If I was depending on the seismic only, so just pure random forest, it doesn't do particularly well down there, okay? It's actually the kriging component, the embedded model that's got a, yeah, hey, we're really strong. But kriging itself is fairly weak in the channel zone because it doesn't krig, okay? And the seismic only helps you a bit. So that's why there's a lot of noise still. And you know, again, one of the things that we can do, if you've got an object model or an MPS, you can always consume those. So, you know, and then kind of add extra things like a user-defined object as well. So you can modify your input models of any variety and kind of create little scenarios around it.
Thank you.
Other questions? Ilnur?
Ilnur Mehmetov from BHP. Thank you very much for your presentation. So the conditional distribution at each location is very important in this work, right? How do you know that the conditional distribution that you create is actually right one? Like, have you done any tests with known distribution at each location, not stationary, bimodal, and then having some synthetic drill holes, and then trying to calculate from random forest those conditional distribution and compare with true conditional distribution? So those checks that ensure you.
Okay, I mean, as in most things in the universe, you're standing on the shoulders of giants. There's tons of work on random forests and about the idea of whether they condition themselves, okay, and whether they reproduce the histograms and so on. There's Bio, I think the guy's name is, who's written lots of papers on GANs as well, on the theory of GANs, has done lots of work on the theory of the random forest, okay, and those convergence. So theoretically, it's well established, well proved. Now, the spatial case is kind of weird, right? Because at any data location, there isn't any conditional distribution. There is no random there is no random function. You know, geology is not a random function. And so the idea that somehow I should be responding to some correct histogram is a little bit weird. But what you see is I'm doing essentially the right thing. I tried to show that in areas where it's channel, I am producing a distribution which is bimodal. Because I don't know if it's channel or not, but I know it's nothing else. Okay? Whereas if you do a Gaussian model, you're going to get a kind of splurge. Everything, you've got all possibilities. You'll get channel values, you'll get non-channel values, and you get everything in between. This one kind of goes, it's bimodal, right? So it is picking out the right kind of things in the right place. I've done tons of tests on this myself. I mean, I can't show loads of it now. But, you know, for the most part, it does reasonably well. I'm not saying it's perfect, it's not. But it's kind of, I think, good enough to kind of, you know, put out there and sort of say, it's worth having a go. That's as much as I can sort of say, really, about it.
Hi, Colin. Thank you very much. Really waking up talk. Can you maybe expand back on the entropy you mentioned earlier with this enforcing scenarios when you start basically bringing information? Some of them, this information would be relevant. Some of them may not be relevant in terms of the impact. So if you can comment how that affects the entropy distribution.
Thanks, Vasily, for the question, but I'm not sure I quite understood. Do you mean the slide that I showed with where I was using the Markov random field, or do you mean later on?
Right. Yeah. With the Markov random field, yeah, that's probably the start.
I mean, I think it's a fairly obvious thing in a way, right? We're dealing with an ill-posed problem. Okay, we know that the set of quasi-solutions for an ill-posed problem is going to be far larger than the set that are actually good solutions. Okay, and if ever you've solved an ill-posed problem without any regularization, you know that you end up with something that's got tons of noise on it. Why? Maximum entropy. Of all the realizations, it's finding the one that kind of does what you've asked it to do, that is maximum entropy. Now, okay, you give it more control. You say, okay, I'm only going to allow you to be in the following 20 different types of models. It's still going to, if you have to choose one at random, it's still going to find the one with maximum entropy, right? So unless you know the actual geology, you're going to be living, and you're somehow magically able to select from the set of all possible realizations which matched the target problem, your forward model, or your forward model data. It's always going to be the maximum entropy in whatever class that you've given. And there's absolutely no reason under the sun that set of models is going to be the true geology, okay? It's not rocket science.
So, yeah, just follow up on that. So when you start enforcing between different, the input features, additional input features of your choice, some of them would be relevant for whatever reason, but you may not know it a priori. But I believe the the technique, the random forest, should enable you to evaluate this impact.
Yes, absolutely. And that's why I said it's very difficult to find a variable that's an intervention variable that you shouldn't have put into the random forest to start with. But the random forest has got a limitation, okay? Is that I've only trained at the data location itself, okay? So I might have a seismic attribute, and I'm being slightly woolly here, but if I've got a seismic attribute and I calculate the correlation with my porosity, I might get a very low value. Now that doesn't mean that the seismic attribute doesn't have some signal in there. It's just that a linear correlation is a terrible measure of it, and capturing it at a point-by-point basis is not the greatest thing. So giving it a kind of to be rude, give it a kick in the arse by switching up the correlation slightly, no, not the correlation, the forcing, the intervention, allows it to kind of say, I'm going to push this seismic a bit more than a linear or the linear method that I've got is allowing it to do. All right? I mean, there are limitations to the random forest. It's still learning at one point. And that's why there's an idea.
Okay, thank you, Colin. Thanks for the questions.